Okay, welcome everyone. Today's tutorial is going to focus on taking one of the standard OpenFOAM tutorials and tweaking it such that you can solve a different problem. So up until now we've focused on the lid-driven cavity, as you recall, and what we're going to do is take that same mesh and the same solver and try to solve a fundamentally different problem. So instead of a lid-driven cavity, maybe we want to solve for channel flow. We have a square channel, for example. This is a standard approach when solving problems in OpenFOAM is to first decide the solver and then look in the tutorials that are available for that solver for something that most closely resembles the problem you're trying to solve. So if for example, we know we're going to use the icoFoam solver and we have a square channel, then this square cavity, the lid-driven cavity problem is our best candidate. So what we'll do is we will copy, first let me load OpenFOAM. We will copy this cavity folder and we will call it channel flow. So now I've got a folder called channel flow. It's an exact copy of the cavity folder. If I decided to run the Blockmesh and the icoFoam solver, then I'm going to get obviously the exact same results. But we're interested in taking this and again modifying it to be let's focus on a square channel with flow into the page. So the first thing I'm going to do is remove and delete all the time folders. And let's start exploring some of these files here. So again, in the system folder, we've got our control dictionary file. Let's take a look at that. We're still going to use icoFoam. At the end of this tutorial, we'll give some examples on using a different solver and how to make that work. icoFoam is, as you recall, is a laminar flow solver. It is a transient flow solver. If we're talking about flow through a pipe, a square channel, we don't necessarily need the transient aspect of it, but for the intents and purposes of illustrating how to use the tutorials to your advantage, we'll keep with the icoFoam solver. The start time, the stop time, we really don't know at this stage if those are going to be adequate or not. So we'll leave this file alone for the time being. But let's just take a look at some of the other ones. Can't change RPG edit. The schemes are all consistent with what we want to do, and the final file here will be the solution file, and this gives our tolerances, the number of correctors, etc. We're comfortable with that as well, so there's nothing in here that we have to change in this system folder. So let's go into the constant folder, and this is where our Polymesh is going to be. Let's open up transport properties first, and as you recall, this is just the viscosity. So we have 0.01. This is meters squared per second. We'll leave that alone as well. And now let's go into the Polymesh folder. As you recall, some of these, all these files, with the exception of the Blockmesh dictionary file, are created as a part of the Blockmesh command that we're going to run here in just a minute. So the only file that we really need to worry about here is the dictionary file. And this, we gave 8 vertices that then defined our block. And we're going to use all 8 of those to use a hex element. And in this lid-driven cavity problem, we had 20 elements in the x and y direction and 1 element in the z. And so one thing that we're going to have to do here is change this dimension. And this is converted to meters, so maybe we have something that is 1/2 meter long. And if we didn't modify anything else, then it would give us a domain that is the right size, but it would only have 1 element in that streamwise direction along the length of our channel. And so we want to change this. We definitely want to change this to be something much larger. Maybe we'll try 50. Okay, and then the other thing we need to do in this file is change the boundaries. So for the lid-driven cavity, we had a moving wall, we had a fixed wall, and then we had front and back. What we're going to do is modify this, because now this top wall is also going to be part of the fixed walls. So now we've got the 4 outer surfaces that are all no slips conditions, so those would be our walls. We don't have a moving wall, but we are going to have an inlet. So let's change this from moving wall to inlet. And we need to change the type of boundary here from wall to patch, and the faces that the face that we're going to use for the inlet, it will be this one that we normally had as empty in the 2-dimensional lid-driven cavity problem. So now we've got our inlet, and we're going to do something similar for the outlet. And we want this also to be patch type, and we're going to change that from the face that defined our inlet to the additional face that again used to be this empty face that ensured that we were looking at just 2-dimensional flow for the driven cavity. So this is now becoming a 3-dimensional problem. We've got square geometry. We're forcing the values to take or the types of faces to be no slip conditions, the wall types for the 4 bounding cases, and then the inlet, and then the outlet. And we can, since we're defining all these faces, we can simply get rid of this front and back definition and then save our Blockmesh dictionary file. And now we've got to go into the initial conditions file in that 0 folder and change, and well, not change, but update all the definitions for pressure and velocity, because right now they're based on the old definitions of what was a wall and what was a moving wall, etc. So I could at this time run the Blockmesh command, and it would generate the mesh for me. But before I do that, I'm going to go into the 0 folder and my pressure, the units of meters squared per second squared. This is pressure divided by density. And so the definitions here are all the old ones. So we've got moving wall, fixed walls, front and back. So we'll get rid of the front and back since we're not using that. Change the moving wall to inlet, and the pressure that we want to supply here is going to be 0 gradient, so that's fine. but we want to have an additional boundary defined as outlet, and its type is going to be a fixed value. And then we need to specify the value, which will just be a uniform pressure of 0. So we're going to basically have gauge pressure of 0 at the outlet. Okay, and that basically sums up the modifications we need to make to the initial pressure field and the boundary conditions for pressure. And let's go do the same thing for the velocity. And we've got the inlet. And in this case, we had the moving wall was going in the x direction, but given the domain that we've just created, we want the velocity into the page, which would be in the z direction. So we can normalize it, or we can initialize it with a full velocity field of 0, that's fine. But we want the predominant direction of velocity to be in the z direction. We got the fixed walls, they have no slip, we're just missing the outlet. And the type here will be 0 gradient. And we've got our fixed walls and then our front and back, which we can again simply delete. So now we've successfully modified the velocity boundary conditions, the pressure conditions. Our block mesh is defined appropriately. We should be ready to run this channel flow. And so we'll first type the Blockmesh command. We can do a check mesh just to verify that everything looks appropriate. We could also go into ParaView here. Even though we haven't run the simulation, there's not going to be any velocity available to plot, obviously, but this now gives us the error that exists. So we've done something in the pressure boundary. We don't have a patch filled for fixed walls. So let's go ahead and go into the pressure, and again this was on from line 25. Inlet, outlet, fixed walls. Let's open up our constant folder. Polymesh. Blockmesh dictionary. And I'm going to type the and sign here because I'm going to open up a bunch of files, and I want to. If you've noticed before, when we just open up a file, then we have to close that file before we can come back to the terminal window. Just typing an and sign afterwards still gives you control over your terminal. So let's see. So we've defined inlet, outlet, and fixed walls here. If we go to the pressure file, we've got inlet, outlet, and fixed walls. So we have all the definitions right. Oh, this is silly. The thing I didn't do is forget to close with my brackets. So let's try that. Let's go back up here. Let's run Blockmesh again. And the error came when we tried to view this thing, so let's open this up. And again, if I type the and sign, then I'll be able to run ParaFoam and still have control of my command window. Oh, you'll notice something here that's you should probably take note of, that when you run ParaFoam and you open up ParaView, then it creates a temporary file, and this file is basically 0 bytes, but the title of the file is what enables you to point it towards all the subfolders that exist in this directory for ParaView to plot things that you want. So another workaround to this is just to, for instance, if you're running multiple simulations, you can then just create a dummy file, call it whatever you want, but make sure the extension is .openfoam, capital F, capital O, capital A, capital M. That will enable you to have those files that point to the appropriate locations, just that it permanently exist instead of this temporary. So we come back here, let's try to view it now. Okay, so we've got our domain, which is a square domain, and let's take a look at the surface with our edges. So here's a view of the mesh, and just to make sure we did these correctly, we'll take away the internal mesh, and let's just take a look at the inlet. There's our inlet, which is at z equals 0. You see what these axes here. And then if we also look at the outlet, then this all looks good. Let's take those away, and let's look at the wall group that we made. And this is a hollow square tube, so everything looks legitimate, looks good. So now we can simply run the icoFoam solver. And as you recall, we decided to just use the default values of a half a second. We've got a mean and maximum current numbers here of 0.5 and greater than 1. This is probably going to be just fine. But if we wanted to ensure that we weren't exceeding the maximum value, then we would have to go and change the time step. But let's go ahead and take a look at the results. We see we have something at the inlet that is a uniform velocity coming in, and that will eventually transition to something that looks like this. If we take a look at the velocity profiles, if we take this and, well, let's look at the centerline velocity first. So if we center this in both the x and y, and then go from 0 to the length of our domain and the z, then we'll see the velocity. Let's take the pressure off just for a minute. So here's our centerline velocity. It starts at 1 and increases up to a value just above 2.07. And so once this flat lines out, then we've reached steady state, or a fully developed solution. The pressure as well in that entrance region has a 0 gradient condition, and then it transitions to this linear behavior. So we could take this and we could calculate the friction factor, for example. Let's go ahead and save this. Let's call it results. And for reference, we saved 100 points in between 0 and 0.5 in the z direction. Let's also take a look at the velocity profile. So let's go down to a downstream distance somewhere just before the outlet. So we'll go 0.45 and then 0.45. And then in the y direction, let's look at the okay, good. So this is a parabolic profile that's transitioned to a parabolic profile, which is exactly what we expect. Maximum in the center, no slip on the sides. and the pressure profile across that cross-section is just some constant. And as I change the location of this, then the velocity profile shouldn't change, but the pressure will shift. And it's hard to see in that because we had a very different value for pressure, but velocity profile remains constant because we're fully developed, and the absolute value of the pressure is changing as we go along, and eventually reaches a point of 0 at the outlet because that's what we defined in our boundary conditions. Okay, so we could take this these results, and we could, we don't need any of these. You see the x and the y velocity are numerically equal to 0. So we've got our pressure, our z velocity, and the distance along that center line. Okay, so what we could do down here is we could define ourselves a L in the x, L in the y. These are both equal to 0.1. So our perimeter, our wetted perimeter, is going to be equal to 2 times the sum of these. And the area is going to be equal to, is the product of these two. And then our hydraulic diameter is going to be equal to 4 multiplied by that wetted perimeter, or multiplied by the area divided by that wetted perimeter. So in this case, our hydraulic diameter is going to be equal to 0.1. Our viscosity, the constant in the transport properties file, it was 0.01. And then our inlet velocity was equal to 1 meter per second. Let's put some units on here just for our own reference. This is going to be meters squared. And oh, this is that one. This is just meters. Perimeter's meters, and these are both meters as well. Okay, so then our Reynolds number is defined as our average velocity, which in this case we have a uniform profile coming in, so 1 meter per second is our average velocity, multiplied by the hydraulic diameter, divided by the viscosity. It's important that we at least look at this because we're using a laminar solver. We should verify that the flow is indeed laminar, and Reynolds number 10 is a few orders of magnitude below anything that's close to transition Reynolds number. So we're safely in the laminar region. This is a Reynolds number, so it's unitless. And now let's do take off a few data points from our data over here. We have some pressure difference. We're going to eventually calculate our friction factor here. And we have, I'm just going to choose these kind of arbitrarily, but I want to make sure I choose them well inside the fully developed region. So I'm going to say that anything past 0.2 is in the fully developed region, so I'm going to go a little bit further. I'm going to go from 0.3 to 0.45. So that dz is going to be 0.15 meters. And the pressure per second squared. The units of pressure again, I should put this this is actually a pressure, a Pascal divided by the density. So in some of the other solvers, the units of pressure will be Pascal, but in this in the incompressible flow solvers, this is the nomenclature that's used. So I'm going to go down until I see a pressure at a distance of 0.35. And from that I'm going to subtract the pressure at, it should have been that's going to be 0.1 then. So I'm going from 0.35 to 0.45 at a distance of 0.1 meters, and that's the pressure difference that I get. So in order to calculate the friction factor itself, then we will go to the definition of the friction factor. There's a standard definition for the fanning friction factor. And here's our definition here. So this is the shear stress, the wall shear stress divided by the dynamic pressure. That's a 1/2 rho u squared, where u is the mean velocity. And we can relate that shear stress to our pressure via the following equation. We just take that shear stress and multiply it by the area, the interface area between the fluid and the wall, which is just the perimeter, the wetted perimeter multiplied by the length. And take that quantity, which is now a force, and divide it by the cross-sectional area of the channel. And that is going to equal the pressure across a certain length. And we solve this for shear stress, and we get the following expression. And we can substitute that back into the friction factor expression, and we get the following here, where we're now, instead of the shear stress, we're now dependent on the pressure difference. And we're going to use this in conjunction with a Reynolds number, which is just velocity times our hydraulic diameter divided by viscosity. Hydraulic diameter is just 4 times the cross-sectional area divided by the wetted perimeter, and so we'll input that here. And we solve this expression for velocity as a function of this Reynolds number. We'll take that and substitute it back into the friction factor expression, and we get the following. So here's our expression for our friction factor. So notice I took the u squared, took one of the u's, and replaced it with this Reynolds number dependence expression, and we get the following. And a lot of times you'll see the friction factor expressed in terms of the product of F and the Reynolds number, and that will be a constant for laminar flow. So for certain geometry, then that product will be a constant number. So when we can now take each of these quantities, our pressure difference, I'm dividing it by density here, and I've got my area, I've got my wetted perimeter, and then these parameters are all parameters that I know. So I can come back to my spreadsheet and begin to calculate these. So this friction factor is going to be 8 times my pressure difference multiplied by area over the perimeter squared multiplied by my average velocity divided by my viscosity and the length. And the length in this case is going to be that dz term, because that is the pressure drop that's the length that my pressure drop is tied to. So we get a value of 14.1, and we can look online for a square channel. friction factor. And you'll see that here's our definition of the fanning friction factor for a round tube. This is what we expect, so move the Reynolds number over. We expect 14.227. So we have an expected friction factor. We are fairly close even with this very coarse mesh that we have. So we can come back now and refine the mesh and look at mesh convergence, or the GCI, for example. Let's do one more. I'm just going to come in here to constant and the Blockmesh file. And instead of 20, 20, and 50, I'll just double each of those. Save that. I've got to come back out and run the Blockmesh command again. And then everything else should just be the same as it was before. And I could potentially run into a problem. Looks like I'm running into a problem already. The Courant number is greater than 1 for the mean and the max. It should be blowing up here in just a minute. I'll go ahead and pause it and come back to it in just a minute. So we're back, and really it didn't take too much longer. The current number kept getting larger. We only reached a time of 0.115, so we've obviously got to go adjust our time step. This is always an issue with transient solvers, and it's important to realize that we don't necessarily need to have that functionality in this problem. We'll go and do this with another solver here in just a minute, but for illustration purposes, let's go ahead and go into the system folder and the control dictionary. And here I'm going to decrease this to 0.4, and I'm going to decrease my delta t down to maybe 0.2. Actually, let's go to 0.1, so 1 millisecond. And in each of these cases, I don't want to write every 20 time steps. I'll write every we'll do 200 time steps. There'll be 400 time steps total, so let's do every 100 time steps. And that'll give us the same output folders. So I'll save that, and I should be able to run icoFoam again. And we'll just watch it for a few iterations here, just to ensure that it's not growing with time, the current number. Okay, so I'll go ahead and pause it. Okay, so the simulation is finished. It took 319 seconds to get to a total time of 0.4, stepping in 1 millisecond increments. So you'll notice in our folder we've got the results there. We can open up ParaView. And again, we want to take a look at this line plot. Make sure we get at a time step that is not the initial conditions. And you'll see that the results, oops. we can save the data again. And we'll go here and open these up. Just for comparison purposes, we'll look at how close we are to our previous value of our friction factor. And so because in ParaView I specified the same number of points along the same length of line, then even though I had a different mesh resolution, you'll see I have the same number of points here, which is 100 points. So all I really need from this is the pressure and the velocity. And let's go ahead and put that in here. I'm actually going to cut this, move things around just a bit. And looks like I grabbed the wrong velocity here, so we better go back. Alright, so I've got P and then P refined, and then I've got UZ and UZ refined. Okay, so now we can just insert something here. I'll do that. So you can see, based on this new pressure from the column, from the refined data, column B, I get a slightly different pressure over that same change in length, over that 0.1 meters. And so my friction factor now is 14.193 instead of 14.09. You can see that it's approaching the analytical value that we could find if we analyze this this PDE and developed our own expression for it. So if we refine the mesh even further, we could do a GCI study, and we can look at other parameters too, not necessarily the friction factor. But if we want to look at the entrance length, for example, we could then identify the downstream distance at which point the centerline velocity doesn't change more than X%, whatever that percentage is. And we could say that's how we're going to define the entrance length, and then we could do that for all three meshes, and again do GCI on that. But this is kind of a brief overview of how you can take a tutorial case and adapt it to a different scenario. And in this case, it was the only thing that it really had in common was the fact that there was a square there. So we could have built this from scratch very easily. It's not very hard to make a single block and fill it with uniform mesh in all three directions. So, but the point of this exercise is to show you that the process in taking some tutorial and then trying to tweak it. So the other thing we could do here is, let me close this too. The other thing we could do is change our solver. So for example, I've been using the icoFoam, which again is a transient solver. Another solver that might be of interest to us is simpleFoam. This is a steady state solver, uses the simple algorithm, but we don't have to worry about the time step and the current number and those sort of things. We need to worry about stability and using relaxation factors, for example, in the simple algorithm. But as you'll see here, it's actually much quicker to do it that way, even for the same mesh count. So what we'll do is the first thing is go into the location where OpenFOAM was originally installed, and go to the tutorial section, incompressible, and instead of going to icoFoam, now we'll go into simpleFoam. And probably the best one to take a look at this would be the PITS daily. So I'm going to copy that, and I'm going to put it back in my folder where I'm working, and I'm going to rename this channel flow simple. Okay, and now let's go take a look at some of those files here. So you'll see it's got the same hierarchy, same folder tree. We've got the 0 folder, the constant folder, and the system folder. But as I go into one of these, let's go into the system folder first. And open up the control dictionary file. The application is simpleFoam. This starts from is right now it's listed as latest time. This is nice because if you run a simulation and you want to tweak one of the settings, maybe the relaxation factor or something else, maybe the tolerances, and instead of running from the initial conditions, it'll just look for the most recent folder in that tree and start from that, and use that as the initialized results. In this case, this is a steady state solver, so when it's listing start time and end time, what this really means is the iteration number. And so going from 0 to 1,000, this gives me my maximum number of iterations in the outer simple loop that I'm going to allow in this simulation. And once I reach convergence, though, it's just going to kick out of this loop, which is something we didn't really have with the icoFoam solver, right? We specified, the way that we had it set up at least, we specified the overall time that we wanted to run the simulation and the time step, and no matter what, it was going to go through all those time steps, even if the change between one iteration and the next was so small and insignificant, it was basically steady state. So in this case, again, it's a steady state solver, so it's going to kick out of the loop once we've reached some specified tolerance. In this case, this is our delta t, or quote unquote t. This is always should be set at 1. And in this case, we're writing every 50 iterations, or in time steps in this case. So the rest of these functions, we'll get into at a later date, but a lot of some of the tasks of analyzing the data that we've done so far, such as find the friction factor, for example, could be simply built into the control dictionary so that it loads these for you. We're not going to need it in this case, so we'll just delete that. And let's go ahead and look at the finite volume schemes. And so it lists all the schemes, just like with icoFoam, what we're going to use for the gradient, for the divergence. And there's nothing in here that we're going to change, but just wanted to show you the format of the file is similar. And then for the solution file, here's where our tolerances are built in. We're going to leave them at the default values. You'll see that there's some additional parameters in here. There's K, epsilon, R, and nu tilde. These are tied to turbulence parameters. If I go into the constant folder, you'll see that I've got an additional file. So I've got the transport properties, but I've also got this RAS properties, which are the properties for my turbulence models. And so let's open up that one. And you'll see right now the turbulence model is set at K epsilon. I'm going to change this to laminar because I know I'm going to be operating in a laminar regime. Turn off the turbulence and turn off the print coefficients option. I'm not going to need any of those, obviously. And then if I look at this transport properties file, I've got my viscosity just like I had before. The first thing I'm going to do is change that to be equal to the viscosity I had in my icoFoam simulations. But because I'm using a laminar model here, even though it's a turbulent simple solver, all these coefficients are going to be they're not going to impact the results at all. So I could go in and change these to 0, but changing the settings to laminar as opposed to k epsilon or some other turbulence model in effect does the same thing. So in the transport properties, in addition to material properties, you've also got the turbulence parameters and values for them. Okay, and if I go into my Polymesh folder, you see it's similar to the icoFoam setup. I just got this Blockmesh dictionary. I could open this up. And you'll see that this particular example is much more complicated than we need. But just recognize that this is really the same type of file as we had before. So just because we're using a different solver doesn't mean we couldn't use the same block dictionary file. So I'm going to go to my previous channel flow simulation. Actually, I wanted to be in the other one, didn't I? Oh, no, that's right. And then I'm going to go into the constant folder and that Polymesh folder and that Blockmesh dictionary. I'm going to copy that I'm going to copy that file to the location of my simple Blockmesh, and it's going to write over whatever file was there before. So this would be in constant Polymesh. Oh, I could have just gone in that directory. Oh well. So I go into that folder and I look at my Blockmesh this time, and this is the same Blockmesh file I just imported, so it's got the same boundaries, my inlets, outlets, fixed walls, etc. I don't really need to do anything different there. So I'm all set to go to create my mesh, but I do need to go into there's still a 0 folder there, so I need to go into here, and you'll see that in addition to the density and velocity, I've got the additional parameters for my turbulence initialization. So I could set all to 0, but again, because I have the settings set at laminar, it's not going to they're not going to use any of those files. So if I look at my pressure, this is created according to the boundary fields that that were set up in this Pitts Daily tutorial, and the same thing with the velocity. And I could go through and change these one by one, or again I could change directories to the 0 folder. I want to go here. So and then I want to copy these guys to my channel flow simple 0 folder, and then I want to copy the U there as well. And I'll go back to my simple 0 folder. And if I take a look at my pressure now, this is my inlet, outlet, and fixed walls, just as I had before. And same thing for my velocity. So at this stage, I have my boundary conditions set up, and I have my mesh ready to create. So I can come here and Blockmesh. Well, this is my finest one, isn't it? Yeah. This is the same, the fine resolution that I had just a minute ago for the icoFoam solver. Let's go ahead and take a look at the mesh and make sure it loads properly. I can come in here to my inlet and take a look at my outlet, and then my wall group. This is good. So now I'm ready to run simpleFoam. And you'll see this going through time steps, and it's solving for the 3 velocities because I got a 3-dimensional case in this situation. It's going to save every 50 time steps. So we're almost to a point where it will save me 1 file, and then very soon after that it will kick out. I think this should kick out maybe about 100 or so time steps. But once that happens, I'll have all those folders. I'll have every 50 folders, and if I wanted more, I could go in and change those. I could look at the convergence rate. I could look at any number of parameters that I want to. So it's done in 85 iterations. I can now look at the solutions. And you'll see that as I step forward, this is not really time, but it's iteration number. So grayed out over here is 50, and then I go to the next one, and it is 85, which is where my solution ended. So I have 2 folders in my directory of data, and 85 is the one I want to look at. It's the fully converged solution, and I can do the same thing I did before. And look at this line of data. And look, as I change this from my converged solution to a slightly non-converged solution, it might be difficult to see, but my results, even though they qualitatively look real similar, they are indeed different. So I see similar behavior, namely that I reach a fully developed condition, maybe at about 0.2 meters, and so I can save this file just like I did the other. And I've got to come in here to different folder for this results. But again, I specified the same number of points to evaluate this at, so it's all I really need to do is copy and paste those columns. So I've got my pressure, this will be pressure simple defined, and then I will put my velocity right here, which will be this column. Here I've got UZ simple defined. Just copy and paste this whole column over. So you'll see I'm over predicting it now. I was slightly under predicting it. Now I'm over predicting it. One thing that you'll find is that the tolerance levels on the simple algorithm are quite low. So what we're going to do is come in here to the system folder and take a look at the control dictionary again. Oh, I'm sorry, not the control dictionary. The solution here. So if I'm going to take each of these, and just to illustrate the impact it can have, I'm going to take each of the tolerances for pressure. This shouldn't make a difference here. But I'm going to decrease each of them by an order, 2 orders of magnitude. Here's my relaxation factors for each of those parameters. So I'm going to save that, and now when I go out to my main folder for my simple channel flow, and then when I run simpleFoam again, so notice that I've got a 50 folder and an 85 folder. I'm going to run simpleFoam again. All I did was change the solution, finite volume solutions tolerances. So when I run this, it's going to, since it's looking at the most recent one, it's going to pick up the results from the 85 and initialize with that. So you see that was the first mesh time or the first time that it's reporting. And so it steps through, it'll save it at 100, and save it at 150. So again, the only difference between the simulation that's running in the background here and what we just did is I decreased tolerances by a couple orders of magnitude. Okay, so the solution converged. It took 272 iterations. Oops. And so I've got folders of every 50, so 50, 150, 100, 150, 200, 250. And then I'm done at 272, but it also has that 85 folder in there from when I did my first simulation. But it's the same mesh, so it doesn't really matter. Let's go ahead and look at the results now. Look at this plot. And I've got multiple iterations here. I'm going to go to my most recent, which is at 272. I'll go ahead and save that file. I'll call this results new tolerance. I can come in here and open this guy up. And let's see, I'm going to get rid of this file. I'm going to make room here for my pressure and for my velocity. Simple intolerance. There's my pressure, and then I've got my velocity. Tolerance. I'm not using these velocities, I guess, but so now when I come over here and copy this over again, you can see I'm no longer, the mesh is the same between these two columns. All I did was change the tolerances by a couple orders of magnitude. And I got there with 280 something iterations, right? 272 iterations as opposed to 400, I guess is what the the icoFoam took. Okay, so regardless of whatever solver you use, the very first step in the process of solving a problem is to choose the solver and see if you can use something from that tutorial that exists there rather than starting completely from scratch. So hopefully this gives you a little bit of insight to solve the homework problems. You'll notice I didn't do anything with the energy equation. I'm going to leave that up to you to figure that out in the next 2 weeks. But for now, this is the end of the OpenFOAM tutorials. Thanks.